Good evening to all. Welcome to week 7 of tutorial discussion for the electrical machines 2 course. Yeah, sorry. Good evening to all. Welcome to week 7 discussion for the electrical machines 2 course. So today we will be kind of discussing the continuation of the last week discussion. So if you remember last week we kind of started discussing the equivalent circuit of three-phase induction motor. Started with single phase per phase equivalent circuit, and we saw how the equations of the equivalent circuit would be, and we derived the parameters of the equivalent circuit. So we'll continue the thread in this week. So we start with the equivalent circuit of three-phase induction motor that will be referred to stator, and we will extend the discussion to the power flow diagram in the induction motor. That was the point where we were discussing last week. So how the mechanical power equation we got. So we kind of, if you remember, we kind of started with the discussion of assuming a fictitious motor and then actual motor. Eventually, they both are having the same rotating rotor field. So that's how we derived the equivalent circuit. Now let's continue the discussion. I'll be drawing the equivalent circuit again, so just so that you'll remember what exactly we have the exact equivalent circuit which we have come up with at the end of the last week discussion. So it's combining the both stator side as well as rotor side. So we are referring the rotor side parameters to the stator side using the turns ratio. So the input will be, if you're assuming the input to the stator is V1, and the rotor resistance R1, small R1, yeah. Sorry, stator resistance is R1 and stator leakage reactance is X1. And we have a magnetizing branch, that is XM, capital XM. And now coming to the rotor side, here the parameters we are referring it to the stator side. So if A is the turns ratio, to refer any resistance or impedance quantity to stator side, we have to multiply with the square of the turns ratio. That derivation, that small derivation we have seen last week. So I'm just writing it here. So first we are writing the standstill leakage reactance X2 multiplied with the turns ratio, that is A square. And this is the resistance term, this is A square R2 by S. So I hope you understand the logic behind the A square R2 by S and standstill reactance having the not having the slip term, but the resistance having the slip term. So yeah, that's how we kind of modified the equivalent circuit to have R2 by S term. Yeah, that's all the last week discussion. So yeah, this is the final equivalent circuit. Now this is the stator referred. I'm writing it here. Equivalent circuit referred to stator three-phase induction machine, and of course this is a per phase equivalent circuit. The same concepts are applicable for three-phase as well. Now if you see the R1 X1 and R2 X2, these quantities are very small when compared to the magnetizing branch XM. Yeah, very small when compared to XM. The reason also we have seen last week, the amount of current required to magnetize the core will be much more than these small rotor and stator reactances and resistances. Yes. Yeah. So now we are kind of trying to simplify this equivalent circuit of induction machine. If you see this parallel branch in between the XM, it's kind of difficult to solve any equivalent circuit having a parallel branch. So we are trying to do the Thevenin's analysis at this point, and it will be much more simplified uh, to work with the Thevenin's equivalent rather than having a resistance and reactance in parallel with the magnetizing branch. So if I pick this particular point and this point, naming it as X and Y. One second. Yeah, I'm naming it as X and Y. Now at this point, if you look from this side, yeah, from right to left, we are looking at it from this point. So here is the I from where I'm looking at. Yeah, so this part remains same. The rotor part is square x2. Uh, yeah, this is not, yeah, x square is 2 dash and s square r2 dash by s. Yeah, so from if you are looking from this side, so we are trying to do a Thevenin's analysis. So if I do Thevenin's analysis, this total branch would be, so the input is V1 and R1 X1 in parallel to XM. So Thevenin's equivalent would be a Thevenin's input voltage, that is VTH, and ZTH would be the Thevenin's impedance. In that I am splitting it as a resistance part as well as the impedance part. So this is RTH and this is small xTH, uh, and the rotor part remains as it is. This is small RTH, this is small xTH, and this is a square x2 and a square. Yeah, you can call a square x2 completely as a x2 dash, and yeah, a square r2 will be r2 dash. So this I am just writing it as x2 dash here, and a square r2 will be r2 dash by s. So if you relate it to a machine, actual machine, this will be stator side, this is rotor side, and it be in between there will be a air gap. This is air gap. We are looking at stator, air gap, and the rotor side. Yeah. Now the last week we have seen, so this particular current flowing through the rotor is I2 dash when referred to the stator, right? So this is I2 dash. So since it's a series circuit, the same current flows through the entire circuit, I2 dash. Okay. Now if I just applying the basic circuit analysis concepts, and if I'm trying to, if I want to try to find the Thevenin's voltage as well as the Thevenin's impedance, so what would be the values would be Thevenin's voltage VTH is equals to, now this particular circuit which we have simplified to Thevenin's. So V1 is the input, and at this point we are trying to XY, right? XY. If you look at the voltage across this branch XY, so the Thevenin's voltage would be input voltage, that is V1, multiplied by that particular branch impedance, that is JXM, now divided by total impedance, that is R1 stator resistance plus JX1 and XM. I'm writing it as a single term. So this will be the Thevenin's voltage, and ZTH will be RTH plus XTH, that we already written as RTH and XTH. Yeah, but actual values of RTH and XTH would be what? RTH plus JXTH. Yes, and actual value of RTH plus JXTH. So how do you solve it? So you just short the voltage source and find the resultant impedance. So R1 is in series with X1 and it's in parallel with the XM. Yeah, it's simple parallel equivalent parallel impedance, that is this impedance R1 plus JX1 in parallel with XM. So R1, so ZTH would be R1 plus JX1 multiplied by JXM divided by R1 plus JX1 plus XM. Yeah, this is VTH and this is ZTH. And here if you see R1, X1, R2, X2, as we know, they are very very small compared to XM. So it's like a low impedance network is in parallel with a high impedance branch. So what will be the equivalent impedance will be? Like what will be the order of equivalent impedance? So when a low impedance branch is parallel to a high impedance branch, the equivalent impedance will be of the order of the lower impedance only. Since it's a parallel, 1 by x1 plus 1 by x2. Now the 1 by x1 will be the lower and 1 by x2 will be the higher. So total reciprocal of those would be lower, definitely. Now RTH and XTH are the Thevenin's equivalents, and individually if you see the parallel branches, R1 X1 is parallel to XM. R1 X1 is very low compared to XM. So the Thevenin's equivalents RTH and XTH will be of the same order as of R1 and X1, since the values are very less compared to XM. Yeah. So now let's calculate the important terms that will be related to this machine. Those are power and torque from the equivalent circuit we have here. So how to calculate power and torque of this machine now? If you know the equivalent circuit, all the parameters, and also the current flowing through the circuit. You know the current flowing through the circuit is I2 dash, and you know the voltage VTH. Let's find the expression for the current now. From there we can easily calculate the powers, because power is nothing but I square multiplied by the resistance or impedance. We will see that, but let's first find the expression for the current here. Yeah, VTH is the input voltage, and the total resistance and also the reactances we know. So ITH will be, sorry, I2 dash will be, I2 dash is equals to voltage VTH divided by resultant impedance RTH, XTH, X2 dash and R2 dash by S. So the resultant will be under root resistance square plus impedance square, because R plus JX will be there. So resultant would be root of R square plus X square, right? So here the total resistance is Thevenin's RTH plus rotor side R2 dash by S. RTH plus R2 dash by S plus the impedance we have XTH plus X2 dash whole square. So this is important current flowing in the circuit. So this expression we'll be using it towards all the discussions which we're going to do today. Everywhere in the power derivations and torque derivations, everywhere this will be useful. So yeah, nothing difficult here. I2 dash is the only single current flowing through the entire series circuit. Input voltage VTH divided by the resultant impedance of the circuit will give you directly the rotor current, that is referred to stator I2 dash. So now let's see the power flow diagram. I won't say the exact power flow diagram. We will be seeing the exact towards the end of today's discussion. But now let's just see the approximate power flow. So still we have not discussed any core losses or any mechanical losses. I'm just with this current and also the resistances and reactances we have. Let's see the power flow diagram. Yeah, neglecting core losses. Flow would be from left to right. So left side, I'm having a total input power I'm giving into the circuit, and the extreme right, I will have the output like the net, uh, whatever power we are left with. So we'll see what exactly that power is. But initially, we are supplying some input power to the circuit. That is, if I assume it is a P in input power. So if you see the equivalent circuit, first it will encounter the stator side in the equivalent circuit. So we are having what all components we are having in the stator side. We are having resistance. So if when current flows to the resistance, we will come across the copper losses. So first there will be a bit of copper losses which we are going to experience. So I'm just pointing it in the bottom side. So the arrow mark represents the kind of power we are losing it. So the first encounter, the first loss would be stator side copper losses. So we know the current I2 dash square, and what is the stator resistance? RTH, right? I2 dash square RTH. So this is the circuit we have seen is for the single phase, but the total three phase losses would be three times multiplied this. So in the each phase, the same stator losses will be there. So for three phase, it will be 3 I2 dash square multiplied by RTH. Then comes the air gap. So air gap, next we will have the rotor circuit. In rotor we have another resistance, rotor resistance. Now again there will be copper loss when current flows through it. That is rotor side copper loss, 3 I2 dash square R2 dash, and that's it. We are left with some power. So this is what the gross mechanical power that is available for me to rotate the machine after eliminating the stator copper loss and losing some power to the rotor copper loss. We are now left with the gross mechanical power. The reason which why I'm calling it gross, it will be clearer when we see the exact power flow diagram. Gross means the total power. In this power also there will be kind of losses, mechanical losses, so that we will see in further discussion. Then we will be left with the net power. So gross will always be combination of both useful as well as losses. If we subtract the losses from the gross mechanical, we will be left with the net mechanical. So that we'll see. But now, for now, this is the approximate power flow diagram, and very pretty straightforward and simple power flow diagram. We have the stator side and input power, and first we encounter the stator copper losses. Then it passes through the air gap. Then we have the rotor loss, rotor side, in which the rotor resistance is there. It will cause the rotor copper loss, 3 I2 dash square multiplied by R2 dash, and yeah, and the gross mechanical power. So yeah, so this is the approximate power flow. If you see this air gap here, I'm writing it as a air gap power PAG. So how much is this air gap power if you want to calculate? Once it crosses the stator side, whatever power we are left with is it is the air gap. Now the air gap power, it has to supply to all the resistances that is present in the rest of the circuit. Now from the equivalent circuit, if you see the equivalent circuit, let's go back to the equivalent circuit. So this is the air gap, and what is the total resistance present in the rest of the circuit? That is R2 dash by S. So whatever power I'm going to supply, active power, relates to the resistance. I'm going to supply to the resistance is R2 dash by S. So, but why didn't we consider R2 dash by S when we are writing the rotor copper loss? So if you go by the equivalent circuit, when I'm writing the rotor copper loss, I have just wrote I2 square dash multiplied by R2 instead of R2 dash by S. But R2 dash by S is the resistance. But why haven't I wrote the R2 dash by S instead of that? So the reason is when you are designing a motor, you will have to like R2, the rotor will have some resistance. So that's not something it will vary every time. Once you design the machine, R2 dash is final. So it is a kind of physical resistance that the rotor would have. When current flows to that particular R2 value, then you will have the I2 square, I2 dash square R2 losses. But if you consider the air gap, it has to supply for all the resistances within the circuit, which is in actuality is R2 dash by S, right? So, but rotor winding has some resistance, physical resistance, that is R2 dash. So, therefore, the copper loss in the rotor would be 3 I2 dash square R2 dash, and the total air gap power would be 3 I2 dash square multiplied by R2 dash by S. Yeah. So, here is the expression for PAG, which is air gap power 3 I2 dash square R2 dash by S. Yeah. Yeah, so I'm just doing some rearrangements in this particular expression. I'm just bringing this slip to this side. S multiplied by PAG would be 3 I2 dash square multiplied by R2 dash. So this particular expression is nothing but the rotor copper loss, which we have here it is we have written. Now, so I'm replacing it. S times the air gap power would be equal to rotor copper loss. This is one particular relation that would be important relation, which we'll come back to it later. Now, whatever power we are left with is the gross mechanical power, right? So P gross mechanical would be, so see here we have air gap power. If you subtract the rotor losses from it, you will be left with gross mechanical. So gross mechanical power is equals to PAG minus rotor copper losses. So PAG minus we already have this relation where rotor copper losses are equal to slip times the air gap power. So if I take air gap power common, it is 1 minus S times. So we have another relation which is P gross mechanical is equals to 1 minus S times the air gap power. So these two from these two relations we can write an important ratio between these three quantities, which is air gap power, rotor copper loss, and also the gross mechanical power. If PAG, if you take the ratio of these three, PAG is to P rotor copper loss is to P gross mechanical, it would be 1 is to, so yeah, the relation between air gap power and rotor copper loss is S times PAG. So the factor is S here, and the relation between air gap power and gross mechanical would be 1 minus S. So 1 is to S is to 1 minus S. So this is a very important relation which will be useful while solving the problems, and during even for the gate related problems, this kind of direct formula based problems they usually encounter, and can remember this, or s- even simpler to understand how this relation came. No need to even remember this, but it's very important relation as far as induction machines problems are concerned. So in gate point of view, definitely every year or alternate years you would get at least one problem directly based on this relation. So yeah, now if you see this particular relation, we have a slip term here. Now since it's dependent on slip, and if at all if the machine is in standstill condition, I mean there is no mechanical movement, machine is in standstill. So what will be the slip at that condition? At standstill condition, slip is equals to 1. Yeah, we discussed that uh, previous week. So yeah, in when the yeah s is equals to 1 means standstill, and s is equals to 0 means practically there is no opposing forces. That's ideal condition that usually not won't happen. S equals to 0 means a no load condition. So in induction machine, the slip will definitely be there. So nr can never be equal to ns. So there will always be a slip. If there is an ideal condition, there is no any opposing forces. S would be equal to 0. No load, any no friction, nothing is there. Then there will be this condition. So now standstill condition we are looking at when S is equals to 1. Standstill means the machine is not rotating. So there is no gross mechanical power available for you to rotate something, right? Standstill, no mechanical movement, and no gross mechanical power. So we already know the gross means the total opposing power available at the motor end. Now, out of this total opposing power, only some amount of this will be useful for the load. So the rest of the power would be, we lose it in terms of friction losses, that is mechanical losses. So that then after eliminating those friction losses, we will be left with the net mechanical power, which is actually useful for the load. So P gross is equals to mechanical is equals to P net mechanical plus P friction losses, of course. So if this gross mechanical is the total opposing force, this net mechanical would be, yeah, useful for load, eliminating the friction losses. Yeah. So now we started this discussion after calculating the rotor current. We are trying to calculate all the powers and also the torques expressions. So now we have all the powers. So let's calculate the torque expressions. Now we know the total opposing power, that is P gross mechanical. So what will be the total opposing torque? What is the relation between power and torque? If you know the speed with which the particular machine is rotating, and you know the torque and power, torque is equals to power by the speed. So I'm trying to calculate the T mechanical gross is equals to P gross mechanical, that is power, divided by the speed. So yeah, what will the units of the speed? See the nr, his small nr, it will be the, yeah, mechanical speed, that is in rps, rotations per second. So the 2 pi multiply, when you multiply 2 pi factor with the rotations per second, it will convert into radians per second. If you multiply it by 360, it will be degree per second. So yeah, so nr would be the actual mechanical speed, this actual mechanical speed, that is in rps units. Now this torque would be, now it will be in the newton meter, and power is in watts, and 2 pi ns will be the radians per second. Now we already calculated the expression for gross mechanical, right? So here T, I'm writing this T mechanical gross, that has a total opposing torque, it is electromagnetic torque, T EM, electromagnetic, is it nothing but the total opposing torque, which we are calling it as a T mechanical gross. So from now on we'll be using the expression TEM for the mechanical gross torque. So TEM would be gross mechanical power, which we have the relation before. If I try to write it in terms of air gap power, it will be 1 minus s terms of air gap. So the numerator would be 1 minus s terms of air gap power, and the denominator is 2 pi nr. Okay, now let me just modify this particular nr into synchronous speed. So we know nr is equals to ns into 1 minus s, right? So I'm replacing this nr by ns into 1 minus s. So 1 minus s get cancelled, and we are left with PAG air gap power by 2 pi ns. So TE electromagnetic torque. So the important thing is you have to keep in mind that this is at a particular slip. Yeah, it is not at it is a slip dependent, because air gap power is a slip dependent term, and also this is the electromagnetic torque at slip s. If the slip changes, definitely the torque at that particular slip would change, is equals to PAG by 2 pi ns. So this is the torque expression. So here ns, what is the ns, what is the expression for ns? I think 2 weeks back we have discussed all the speed formulas. So in that ns would be rps, unit rotations per second. The formula is 2f by p, right? 2 times the frequency divided by supply frequency, divided by the number of poles of the machine, 2f by p. So it's a constant. So once you design the machine, the frequency is fixed and also the poles are fixed once you operate the machine. Now 2f by p is a constant. Let me just write it in a separate slide. TE is equals to PAG by 2 pi ns. So here ns is 2f by p. This is a constant. It won't change. And 2 pi is also constant, right? The units of TE is Newton meter, and the units of power is in watts, and 2 pi ns is kind of constant. So now if you see this PAG, usually like is expressed in, that's why if you are just multiplying a factor of which having units of watts with a constant. So usually if PAG is in watts and this is in a constant, so PAG is also represented as synchronous watts. So it's nothing, you don't have to get confused here. So watts is something we know, the power. Now you can also represent this particular PAG eliminating this constant and merging it with the units. Now instead of writing it as PAG by 2 pi ns and calling it as watts per some constant, I can also modify it and write it as simply as PAG, but the units would be synchronous watts. The reason behind writing it is they say that electromagnetic torque is nothing but the air gap power in synchronous watts. So that's what we got the expression, right? TE is equals to PAG if the units are in synchronous watts, and also the torque units is here now Newton meter, and PAG units is synchronous watts. Usually we don't actually see this kind of synchronous watts power usually, but the reason which why I'm telling you is, in while solving problems they might uh, give you this kind of information. So the air gap power is x synchronous watts. So instead of taking that as a individual PAG, you should take that factor as a PAG by 2 pi ns. So then the total synchronous watts is already given to you. No need to again divide it by 2 pi ns. Yeah. So now, yeah, if you look at this expression further, let me just write the expression for power here. TE is equals to air gap power, that is 3 I2 dash square R2 dash by S, that I know. Now divided by 2 pi ns. But we already derived the expression for I2 dash, that is the rotor current referred to stator. I'm writing the expression for I2 dash here, that is VTH divided by total impedance of the circuit, that is RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square. Yeah. Now you just try to substitute this rotor current here in this expression. I'm bringing out the constant terms 3 by 2 pi ns, and also yeah, let's just substitute this I2 square here. So I2 dash square would be VTH square, writing it VTH square here, and there is R2 dash by S in the numerator, and the denominator is already having a square root. If you square it, you will be left with the RTH plus R2 dash by S whole square plus XTH plus X2 dash square. So yeah, this is the expression for electromagnetic torque, 3 VTH square divided by 2 pi ns multiplied by R2 dash by S divided by total resistance, total impedance equivalent RTH plus R2 dash by S square whole square plus XTH plus X2 dash whole square. So this is a relation between torque and also the slip present in the circuit. Now if you see, for every different slip your torque will change. So that's why I wrote previously, this is the electromagnetic torque at slip S. Now as slip changes continuously, your torque will also changes. So what are the extreme values of the slip you can get in this induction machine? Yeah, for different values of slip given, you can calculate the torque here, electromagnetic torque. So if I'm trying to make a lookup table, so what are the extreme values? What are the for every value of slip, there will be electromagnetic torque, right? So the maximum, the values between the slip will vary is 0 to 1. So 0 and 1. So 1 would be the condition standstill, and slip 0 means no load condition. So practically 0 won't happen, but I'm just writing in the extreme condition 0 to 1. So while the slip changes from 0 to 1, you will get different torques. So it's at slip is equals to 0. If you substitute s equals to 0, what would be the torque here? R2 by R2 dash by S is equals to 0, infinite, and by infinite 0, the torque is equals to 0. Even if you go by the logic, s equals to 0 means there is no, yeah, there is nothing. You have starting with s equals to 0, there is no torque you can get. Electromagnetic torque would be 0. Now slowly the slip would increase, let's say zero point 0.1, 0.2, 10%, 20% slip, so on, 100% slip, s equals to 1. So I'm not saying from 0 to 1 if you go, your torque will be also go from 0 to maximum. So the relation between torque and slip is definitely not a linear relationship. Yeah, at s is equals to 1, you will have some torque. So S equals to 1 means what? Standstill condition. Yeah, standstill. At standstill condition, you will have some torque. That is where you are starting your motor. That is the starting position. So that is the starting torque, you can say. So when the machine starts, the slip will be 1, and slowly, if the speed keep on increases, what will happen? Your slip slowly reduces. Yeah. Yes. This. Yeah. So if this is the lookup table I'm saying. So let's say I'm trying to get the relation between speed torque. On the x-axis I have slip, and y-axis I have torque, electromagnetic torque. So from here I'm starting 0 to 1. S is equals to 0 here, and S is equals to 1. So from left to right my slip is increasing, and at S equals to 0 we have some 0 torque here, 0 torque, and S is equals to 1 means standstill condition at the starting condition. So you will have some torque here. So as I increase the slip, uh, slip increasing means you can say the speed is decreasing. So from right to left, if you see, the speed will, yeah, the speed will increase. So at the starting, let's say this is starting condition, starting point, where your speed is equals to 0. As you reach this point, s equals to 0 means nr will be equal to ns. Yeah. So at s equals to 0, you will have 0 torque. As you keep on increasing slip, you will reach, this torque will keep on increasing. At some point, you will touch the maximum, and then your torque will fall, and you will reach a certain point. At this point where it is a starting condition, I would say this is the starting torque. If I It's not like it's getting settled like this. You can draw. Yeah, this is the starting torque. Yeah. So as you keep on increasing the slip, and you will reach some point, this particular point I would say as a TE maximum. So this is the maximum torque point, and every torque has its own slip, and in between some 0 to 1 you will have such point where you will have a maximum torque. So there will be particular slip associated with that particular torque, that I'm calling as alpha. So this will be the slip at which your maximum torque would occur. So yeah, so there is, let's say if you want to find that slip, like if you want to find at what slip you will experience the maximum torque. If you want to find that particular torque, what will you do? You have this, you have the curve, you have the torque versus slip curve, and you already know the equation for the electromagnetic torque here. Now how can we find that particular slip where you can have the maximum torque? Yeah, any curve, if you want to find the minimum or maxima, the basic mathematical standard would be to differentiate that particular curve and equate to 0, and you find the root of the equation. So by differentiating means you are actually trying to calculate the slope of that particular curve. So whenever you have a maxima or minima at that particular point, the differentiation would be, yeah, there you have no slope. The slope would be 0. So then if you equate to 0 and define the point, so then you will find the actual value where you will get the 0 of the equation. So alpha would be Te max, and if you want to find the alpha, you have to get the derivative of this with respect to alpha and equals to 0, and you can find the alpha of it. Now you see the entire expression here, and it's already a second order equation, and it's already having a square, and derivating and equal to 0 will be a tedious process. It is standard form, you will get the solution if you do that, but it's a tedious process. So there is another method where you can actually find the slip at which the maximum torque occurs. even more straightforward and easily? Any idea? So let's get back to the equivalent circuit here. So this is the particular total circuit we are seeing. Let's say consider this particular R2 by S as a load of your circuit, and yeah, yes, this particular equivalent circuit we have RTH, XTH, and X2 dash, and R2 dash by S. That is with respect to slip, this particular R2 dash S, R2 dash by S would vary, right? This is with respect to S increase or decreases, you would get the different R2 dash by S. So we already know that our air gap power in the circuit is dependent on this R2 dash by S. Yeah. Now PAG is something which is directly related to our electromagnetic torque, because PAG divided by some constant, that is 2 pi ns, is nothing but the electromagnetic torque. Now this TE and air gap power are literally dependent on this R2 dash by S term. Now our intention is to maximize this particular torque. So let's come back to this curve. Now we have seen that TE and PAG are dependent on each other. So I am trying to maximize this particular torque. So if I can maximize this air gap power, then I for sure know my torque is also maximized. So in order to make my air gap power to its maximum in this particular circuit, equivalent circuit, I will apply the maximum power transfer theorem. So this particular circuit, if you see, this is the air gap power. I'm seeing it from here. This is the total power supplied to this particular circuit. This is the air gap power. So what does this maximum power transfer theorem say? What does this maximum power transfer theorem say? So this theorem says that whenever your load impedance will be equal to your source impedance, then for sure the maximum power would be transferred from source to load. So impedance matching you have to do. So here my load resistance is the maximum power, so active power. If you see, so this particular total, this particular total impedance is, I'm considering the source side, and this branch, this is the load side, where it's a slip dependent term is there, and now I'm trying to maximize the power flowing through this particular load resistance R2 dash by S. So at what slip my power would be maximum? If I want to find that, I am trying to match this source impedance and the load impedance, which is R2 dash by S. Yeah, so this R2 dash by S should be equal to the total impedance we see, RTH, XTH, and also the X2 dash. I'm taking a fresh slide here. So load resistance, I'll say load impedance is equals to source impedance, where my load is R2 dash by S, but I'm writing it here S instead of alpha, because alpha is the slip at which my maximum torque would occur. Now, if this happens, load impedance is equal to source impedance, definitely the maximum power would transfer, and the slip would be alpha. R2 dash by alpha is equal to source impedance. We have RTH, XTH, and also X2 dash. So the resultant impedance would be RTH square plus XTH plus X2 dash square. So from this relation, you can simply find the alpha. Alpha is equals to R2 dash divided by RTH square plus X2 dash plus XTH square. So this is the slip alpha at which your torque would be maximum. Now what is the value of that particular slip torque? What Te max is equals to how much? So just have to substitute this particular alpha in your torque expression, right? So we already know the torque expression is 3 Vth square 2 pi ns, and we have R2 dash by S. I'm writing S only because this is the torque expression we derived. RTH R2 dash by S square plus XTH plus X2 dash square. Now this would be maximum T max at S is equals to alpha, and I can substitute it 3 Vth square. This term remains same 2 pi ns. So R2 dash by S, R2 dash by alpha. So R2 dash by alpha, if you see, this relation would be under root RTH square, RTH square plus XTH plus X2 dash square. So the denominator would remain same, that is RTH plus this R2 dash by S again. This is R2 dash by alpha. So R2 dash by alpha is again this under root term, under root RTH square plus XTH plus X2 dash square, plus again we have the reactance term XTH plus X2 dash square. Now simple algebraic expressions expansion, this is a plus b whole square, and like this under root is there, and if you just expand it, and you can get RT square plus again RTH square is there, and you will have XTH plus X2 dash square, and simplify it and you will get one common term and 2 times this term below, and I'm taking this 2 this side, 3 Vt square 4 pi ns, so this will be 1 by this will be by maximum torque. Nothing, we just substituted the alpha at which the maximum torque occurs, and then we just substituted the expression here. So see here the RTH in terms of RTH and XTH are there. So if in order to calculate the Thevenin's equivalence of the stator side, you just have to know the value of R1, X1 and XM. So we already know, if you know these three, you can get the RTH and XTH, the first slide we have discussed. So if at all in the question they have given XM is very high, then you can easily neglect this XM, and RTH and XTH would be equal to this R1 XM, and VTH would be equal to V1. So I'm writing it here. If XM is equals to very high, VTH will be nothing but the supply voltage V1, and RTH is equals to R1, XTH is equals to X1. Yeah. Now see, after substitution and cancellation, one important takeaway from this particular maximum torque expression is, so this maximum torque expression, can you see the term R2 anywhere? The R2 dash, which is the stator referred rotor resistance. There is no R2 dash here. So this maximum torque is independent of the rotor resistance. So that's what I want to tell from this expression. So if you keep changing this rotor resistances, like you are replacing R2 with some external resistance, different external resistances, your maximum torque is not going to change, but it is directly relates to your Thevenin's voltage. See, if the input voltage, that is Thevenin's, it is directly related to square of this Thevenin's voltage. Now if you half the Thevenin's voltage here, your torque will go down 4 times, right? So let me just write it here, like Te max is depend on VTH square. Now, if VTH if VTH is VTH by 2, I just half the uh, Thevenin's voltage, input voltage, then TE max would be TE max by 4, square relation we have, right? Now, what I want to show it here is, so let's say, see, another important thing is I've just changed the VTH. So in this I've changed the VTH, but this expression remains same. But this is the same maximum torque you're experiencing at the same slip. This alpha won't change. So if see alpha expression, if you see, it is independent of Thevenin's voltage, right? In this alpha expression, there is no input voltage. So even if you have the Thevenin's input or if you double the input, this alpha is not going to change. So that's what I want to say. If VTH goes to VTH by 2, your maximum torque would go 4 times lower, but your alpha would be alpha only. So if I want to represent that in this figure, this is the slip and this is the torque. Now this is the maximum torque, TE max, and this is slip 0. Now I have this particular maximum torque here, and this is the particular maximum torque at some alpha. And let's say this particular maximum torque you have got at the VTH, at where your Thevenin's voltage is VTH. Now Now I have changed the VTH to VTH by 2. Now you know that maximum torque will be going down by 4 times. So if it is TE max, maybe next I will have this. If this is TE max by 4, this is where you will get the maximum torque. But will your maximum the slip at which the maximum torque changes? That won't change. So this particular alpha would remain same, but your maximum torque would be here somewhere. So the new curve would be like this. Sorry. Okay. Now this particular curve would be for VTH by 2. This curve would be for VTH. Understood? Now both sides you can see the alpha is same. The slip at which your maximum torque occurs is same, but your maximum torque would go down. Yeah. Now we already know this alpha from the alpha expression. If you see, alpha is independent of Thevenin's voltage, but it depends on R2 dash, that is your rotor resistance, which is which your maximum torque is independent of. So I'm writing some key relations here. TE max, VTH dependent, and R2 dash independent. Okay. If you see the slip at which your maximum torque occurs, it is R2 dash dependent and Thevenin's voltage independent. So this particular curve says by changing your VTH, so what would change? This particular TE max would change. We have seen that TE max which is changes. Now we will see what happens to the maximum slip at which your maximum torque occurs if I change the rotor resistance. So that's what you see, right? Even in the last week we have solved a problem where they have inserted external resistance to the rotor. So there in the problem we have seen that your starting torque has improved by adding the external resistance. So that's the added advantage. But what happens when you add the external resistance? Your maximum slip would change. The maximum slip is the slip at which your maximum torque would change. So how would that curve look like? So I'm drawing this curve. This is slip, and on y-axis you have torque. And let's say this is T max line, okay? And this is the starting position. S is equals to 1 and nr is equals to 0. This we already know. Here s is equals to 0. Okay, let's say for particular r2, I am having this particular torque clip. Okay, so this particular alpha, let's say this is alpha 1. This alpha 1 is at r2 dash, for r2 dash rotor resistance. At r2 dash I have the slip alpha. Now what I did, I have inserted a external resistance in the rotor circuit. So the total rotor resistance will be now r2 dash plus r external. Now if you see the slip expression, maximum the torque slip expression, if you change the r2 dash plus r external, now your alpha will change, the denominator also. So now you will get some other alpha 2 for r2 dash plus r external. So there you might have this kind of curve. Okay, this particular curve is at r2 dash plus r external. So I am adding one more resistance of r external. So this time my total rotor resistance would be r2 dash plus 2 times r external. Here we have alpha 2, this is alpha 1. I will have alpha 3 at which my maximum torque occurs. Let's say this is alpha 3, and it will start at 0 and it will reach maximum and it will do like that. So this is for r2 dash plus 2 times r external, right? Now one interesting thing which you can observe from this particular graph is every time I'm adding this r external resistance to the rotor, my starting torque is improving. This is the starting torque initial. This is starting torque 1 for my r2 alpha 1, r2 dash 1. This for r2 dash resistance, this is my starting torque. When I introduced an external resistance, my starting torque went up, and when I introduced double the external resistance, my starting torque even went up. So you are getting high starting torque as you are keep on increasing the external resistance. So is it like like if you keep on increasing the stator like external resistance, you might get one point where your curve will have the starting torque at here, where you'll get the maximum torque itself. So it means, see, at this particular point you have keep on adding your external resistance such that your starting torque itself is the maximum torque. So that's a great advantage, but is it suggestible to do that? My point is, with the default resistance of R2 dash, you got a very minimum starting torque. That is very less. So there we have keep on adding some external resistances such that your starting torque will be keep on increasing. So there exists one particular resistance such that your starting torque would be equal to your maximum torque. So that your machine would accelerate very quickly because you are giving the maximum torque at the starting itself. But if this condition persists, you have added your external resistance to that much extent, what happens? Your losses would be much more, right? At because you can't continue keeping that resistances as you machine runs, because while machine runnings, the R2 dash will have keep like the rotor copper losses. If you see now R2 dash plus this external resistance, right, you will have much more rotor copper loss. So this is not suggestible. The total losses would increase. So that's why what people will do at the starting, you will connect the as much as external resistance so that you will get the maximum torque, and later you will cut it down. Yeah, like that's the logic, that's the concept here. Like you, see, what should be the provision available for you to, in order to do that, you should make your rotor terminals available for you so that you can add and remove any external resistances while the motor operation is happening. Because at the starting you will connect the external resistance such that you will get the starting torque, maximum torque, and you will quickly accelerate your motor, and once it picks up the speed and motor gets running, you will cut out the external resistances in order to minimize the losses. So that's the idea of adding the external resistances. So yeah, that's how you will get the maximum starting torque at the starting, as well as you will get to minimize the rotor copper losses. See, so now we will, with this idea of all the copper losses, mechanical losses, and the core losses, we will now have a look at the exact power flow diagram. So we have seen the approximate power flow. Now we will see exact power flow diagram. Now let's say I'm again writing, this is my stator side. I'm giving an input of V1. I'm having the resistance R1, stator resistance. I'm drawing the exact equivalent circuit. So R1, and next one is the stator leakage reactance. And here I am having magnetizing reactance, and also there is a R naught term, which is the core loss component. Refer to stator, like considering the stator side. R naught is there, XM, and now we are proceeding to the rotor side where we have X2 dash, which is rotor standstill reactance referred to stator, and the branch R2 dash by yes. So this R naught we have drawn it for the first time. So it actually models the core loss that is present in the stator side, core loss component. And now if you look at the actual power flow of the machine, power flow diagram, now we have input power, okay, and initially we will have some stator copper loss, right? PST copper loss, PST is stator copper loss powers, and then we will have this R naught, see stator copper loss, stator core loss. This eddy current, hysteresis losses, whatever your core loss is having, that contributes to the stator copper loss. And then we have reached the air gap here, and here we will have air gap power, and after air gap it will reach the rotor circuit. First you will have, see, rotor core losses are very negligible. Practically you won't have any while moving the rotor. There is no core there, so rotor core losses are usually very negligible. We don't consider it. Rotor copper loss will be there. If at all there is any rotor core losses, they will give it in the problem itself. Usually they are negligible. Even if negligible, they will specify that. Even if they don't give any, you can take it as negligible. This is rotor copper losses. And see, once you have eliminated the rotor copper losses from the approximate power flow, we know the power whatever left here is the gross mechanical, right? P gross mechanical, and then if you subtract, this is gross, now you have to get the net mechanical. Net mechanical power means which is available at the shaft and which is actually useful power for the load. So you have to subtract the mechanical losses. So what are all the mechanical losses in the rotor side? See, rotor is the one actually rotating, right? There will be a lot of mechanical losses. See the net mechanical. So here you have to subtract the mechanical. losses. So in the rotor side, when a rotor is rotating, you will have friction losses and windage losses due to the wind, and also the bearing losses. All these contributes to the mechanical losses. So you will have friction, windage, bearing losses, whatever rotating parts, you will have the mechanical losses. Now, after eliminating all these losses, you will be left with the net mechanical power. So you have given some input, but you are left with the this net mechanical, which is actually useful for the load. So now if you want to calculate the efficiency of this machine, you have to calculate the output by input. Output here is the net mechanical, actual useful power for the load, divided by the total input, P in. Yeah. Now let's say you don't want to drive any load, but you are trying to rotate the machine, but still it will consume some power. So it is very basic. Now even if there is no load, now let's say you have a machine and you have given a supply and some input power you have given to the machine, and its machine is rotating, and if you connect some watt meter to it, it will definitely read some it definitely gives some reading. There will be some power it will be consumed by the machine. So what exactly that power is, by looking at the diagram you can say that. So all the losses that contributes to the machine, even if there is no load, those are the no load losses. So under no load, if you see, stator copper loss will be there. No load current, if you see, so no load current is usually very very small. The current flowing through the windings and all, it's very 10% or 20% of the full load current whatever you get, it's very small, but you have some no load current. Stator copper loss will be there, very less losses. These are stator copper losses because no load current will be very small and you are taking the square of it, I square r. And you have the core losses and also the mechanical losses. So these are the dominating ones. If you see two kinds of losses, this is stator copper loss and this is the core losses and mechanical. Now you can treat these both core losses and mechanical losses as the rotational losses. Now these are the if there is any no load on your rotor, these are the no load losses, that is stator copper loss and core stator core loss, as well as the mechanical losses. So yeah, these are the dominating, these are the no load losses. Now with this understanding, let's solve some circuits. If you could some problems. So there's nothing complex discussion we have done today. We have discussed the exact equivalent circuit of the three-phase induction motor referred to stator side, and then we started with the power flow diagram. Initially, we discussed the approximate power flow, and then we have seen derived the expression for the rotor current, and with that rotor current expression we have solved the bar equations, torque equations, and we have seen the torque slip characteristics and how the Thevenin's voltage as well as the rotor resistance impact your maximum torque as well as the slip at which the maximum torque occurs. So this, and then we have seen the exact power flow diagram. Now with this discussions, let's try to solve these problems, and this will be, if you understand the past 1 hour 10 minutes, 1 hour 15 minutes discussion, this will be very easy to solve, and you just have to take care of the data what they have given in the problem and understand what you were asked to solve, and you will be just direct, easily substitutable kind of questions. So I request everyone to pick up a pen and paper and also calculator with you and solve the problems with me, and we can we can verify our answers with each other, so that I'll also be sure that I'm not making any mistake, and even you can also tally it with our calculations. So we are having a question here. Consider a 10 kilowatt, 3 phase, 6 pole, 400 volts, 50 hertz, star connected induction motor. So all the parameters related to the machine are given. So these are the nameplate details, what they usually say, like on this machine itself, all these details will be imprinted, these nameplate details. So one important thing I want to tell is whatever power that is being displayed on the nameplate details will be its shaft bar. So what is the, it's not the input power, it's not the air gap power, nothing, it's the actual shaft power, that is the net power that is being utilized by the machine to rotate, that is useful power to the load. So here the 10 kilowatt power is nothing but the actual, that is P net mechanical. Okay, yeah. So we were given with nameplate details of the motor. We know how many poles the machine motor is having, and voltage, and also the um, frequency at which the motor is being operated. Okay, now the stator resistance per phase is 1 ohm. Okay, I'm writing it the expressions here. R1 stator resistance per phase, right? This is 1 ohm, and at no load it draws a line current of 10 amps. So we just discussed the no load current is very small, and we were given with the 10 amps. I naught is usually we represent it as a no load current. Full load means IFL, you can take it as that, and then input power of 800 watts. So at no load it is drawing this amount of current and an input power of 800 watts. So we were given with the input power your circuit has to supply under no load condition. So P input no load is 800 watts. Okay. Now at full load we have given with another information. So under full load your machine is drawing a line current of 20 amps. It's just double of the no load current, and an input power of 12 kilowatt. So P input under full load will be 12 kilowatt. Okay. Now the friction and windage losses is 300 watts. So we discussed this. This is the mechanical losses. So mechanical losses were given as 300 watts, and the rotor copper losses at no load. Definitely at no load we are neglecting that. So rotor copper losses under no load condition are negligible, zero. Okay, this is the data which we were given with. So this we will always have to note down each and every data you were given with. And now let's see what we were asked to calculate. So now the question is to estimate the stator core loss. See, you need to calculate stator core loss. You are given with this data. So how can you get this? So the last thing which we have discussed today is the no load condition. So we already know under no load condition your motor will just have to supply to the no load losses, that is stator copper loss, stator core loss, and the rotor copper loss, and the mechanical losses. See, if you see the these four losses, these are the four losses your motor has to supply during the no load: stator copper loss, stator core loss, rotor copper loss, and also the mechanical losses. Now those are all the no load losses, and you are asked to calculate stator core loss. So now let's see, input to the no load losses will be required to losses only to supply the losses. So what are all the losses from the exact power flow diagram we have? Stator side copper loss and stator side core loss, and then we come to rotor side copper loss, and then mechanical losses. Now from this question they already given that rotor copper losses at no load are negligible, so we will neglect this term, and stator copper losses at no load. To calculate this, we know the expression 3I square R1, but this I would be the no load current. This is I naught. And P stator core, this is what we were asked. And the mechanical losses, these are friction and windage losses. They were already given as 300, right? Now, to calculate this input no load, we already given what is the input no load, that is 800 watts. The total is 800 watts. From this is just a simple substitution. Stator core loss would be 800 minus 3 times I naught. How much is I naught square? This is 10 m. 10 multiplied 10 square multiplied by R1. R1 is 1. Yeah, minus 300. So this will be 200 watts. So this is stator copper loss, simple. So the key concept is at no load, your machine has to supply to the all the losses present in the machine. So if you see the complete power flow diagram, there are four losses at no load you will have to supply for the losses. So out of that, it was given the rotor copper losses are negligible. So the rest three losses are stator copper loss, stator core loss, and mechanical losses. Now from that, you have calculated the stator copper loss. Now the next question is, you need to estimate the air gap power at full load. So PAG at full load, you need to calculate. Now, what is your thought process? Like, how would you try to solve this? Because everything you need to go back to your power flow only. So if you able to understand the power flow diagram perfectly, it's very easy to get an idea like whatever power, whatever loss they were asked to solve. Now see, you are asked to calculate the full load air gap power. Now what data you already know, full load related, you know the input full load and also the full load current, and you need to calculate the air gap power full load. So now let's go back to this condition. This is the air gap power which was asked, and you know the input in the full load. And if you if you subtract these two losses from the input full load, you can easily get the air gap power, right? Now the what I'll write is, my input full load power will be equal to my air gap power plus the stator losses, stator copper losses at full load, plus my stator core losses at full load. Anyhow, the stator core loss will be same even in full load or no load. It's not actually dependent on no load, no load to full load. They remain same. Now this is what you have. Now this is what you are asked. Air gap power at full load is equals to input power full load minus stator copper losses at full load plus stator core losses at full load. So then you already know the input power at full load, that is 12 kilowatt, minus, you need to calculate the stator copper loss at full load. What is the stator copper loss at full load? 3I square R, right? 3I square R1 plus this stator core loss we calculated in the previous problem, that is 200. So this 3I square R, this I square would be full load current now. So that's what you need to be careful about. The current what you are using it. What is the full load current? 20 amps multiplied by 1 plus 200. So you can solve it. 12,000 minus 1200 plus 200, 1400. So you can get some watts. You can calculate it. 12,400 into 3, 1200 plus 200 minus 12,000. It would be 10,600. 10.6 kilowatts. This is the air gap power at full load. So the next question is, you have to estimate the rotor copper losses at the full load. Now again, you can go back to your exact exact power flow diagram, and you were asked to calculate the rotor copper losses at full load. Now at full load, you already calculated the air gap power. Now you know the extra term. Now let's go back to the, so this one. Now what you were asked with? You were asked with the rotor copper loss. So this particular rotor copper loss you are asked with. Now you know this air gap, you have to calculate this one, and net mechanical power. So see, in the nameplate details we were already given with the full load net mechanical power, that is 10 kilowatt. So you know this and you know this, and you are asked to this particular, so you just have to subtract this mechanical losses and you can easily get the rotor copper losses at the full load. So let me just write the expression here. P air gap full load, if you know that, if you subtract rotor copper losses at full load and this mechanical losses at full load, you will get the P net mechanical. You were asked with the rotor copper losses, so this one, P rotor copper losses at full load is equals to air gap minus P net mechanical full load minus P mechanical losses full load. So what is the air gap power we calculated? 10.6, 10,600 minus net mechanical power, it's given in the problem, 10 kilowatt. It's a 10 kilowatt motor, right? Now minus mechanical losses. Mechanical losses were already given in the problem, that is 300. So rotor copper losses would be 300 watts. So this is 10,600. This is 10,600 minus 300. 300. It's a simple substitution. That's what I told you. If you understand the exact power flow diagram perfectly, then it's nothing but direct simplification. Now let's see the next question. So now we are asked to estimate the full load speed in RPM. Now see, full load speed you need to calculate. Let's first try to write the formula for full load speed. NFL, that is rotor full load speed, if you want to calculate, it's, if you know the synchronous speed, you can just multiply, like subtract with the 1 minus s, and you can get the full load speed. Now ns, you know, it's 120 f by p. Frequency, you know, poles, you know, 1 minus s full load. So this is what you need to know, that is full load slip how much. So how can you calculate the full load slip? What are the previous problems we have calculated? We know the air gap full load, rotor copper losses full load. See, this is how the gate problems will also be. So it's just simple relations you need to s- able to think at that instant, and it will be very easy. See, all you need is a full load slip. Now these two you already know, so you need to just get a relation between these two in terms of slip, and you can easily calculate. So today in the 0.028, uh, you mean, no, I don't think 0.028. Let me also confirm. Yeah, okay, slip. So the important equation which we have highlighted is this one, the relation between powers and slips. So if you look at this one, the relation between air gap power and the rotor copper losses would be PAG is to P rotor copper losses. It's the multiplication of slip. That's it. Now if you multiply, now come back to this problem. slip times air gap power would be equal to rotor copper loss. This is at full load. This is at full load, you know. Now you can get the full load slip. Now S full load is equals to rotor copper loss at full load divided by air gap power at the full load. So what is the rotor copper losses we got? 300 divided by air gap at the full load. What is air gap? 10,600 watts. So how much is this? Yes, correct. So it is 0.028. So if you see, this is the 2.8% slip at the full load you got. Now, yeah, you got this full load slip. Now you just have to substitute this in the formula to get the full load speed. NFL is equals to NS, that is 120 F by P. This is a 50 hertz motor, 6 pole machine, 1 minus 0.028. So how much is the full load speed? 1 minus 0.028 multiplied by, this is 1000, no? This is 972. This is RPM. See, in the question we already know we have to calculate it in the RPM. That's why we took the 120 F by P. If not, you have to go, if it is in RPS, it will be 2 F by P. So that also you need to be careful while solving the problems. Okay, next question would be, we have to estimate the gross mechanical torque in Newton meter developed at the full load. Gross, you have to make sure you noted that point, is gross we were asked under the full load. Okay, so the simple thing is you just have to calculate the P mechanical gross, and you can see we derived this today. P gross mechanical divided by 2 pi nr. So this is also equal to what? PAG divided by 2 pi ns. These two we already derived it today. Now, since we already calculated gross mechanical, we have not calculated yet, because now if you know you already know the full load slip. It's just multiplied by 1 minus s times to the air gap, you will get the gross mechanical. However, you already know the air gap power at the full load. Now your this would be air gap power at full load divided by 2 pi ns. Ns is in rps here. What is the air gap power at full load you have? Okay, 101. Let's see. 10. Let me also calculate it. We both will tally it. 2 pi into 2f by p. So 10600 divided by, this is 3 multiplied by 3 divided by 100 pi. So if we, this is 106 into 3 by pi. 106 into 3 divided by, okay, we also got around that. Oh, yeah, 101 point. Yeah, I also got the same. So yeah, 101.2 Newton meter. That's correct. Oh, I have wrote it here. Okay. Okay. Anyway, so we need to estimate the shaft torque here. Shaft torque, you know, the output shaft available at the shaft end. So it's simple. It's nothing but the output torque. So you need to get the shaft at the full load. It's just the output power divided by 2 pi n r. So what is the output power? It's already given in the question. That is, it's a 10 kilowatt motor. 2 pi into NR. We already calculated this NR in the previous problem, right? NR, how much you got? NR at full load, 972 RPM. But here it is RPM. It's in RPS here. Okay, 98.25. Let me also calculate. 972 divided by 60. Okay, so 10 into 60 divided by 2 pi divided by 972. How much you got? 980 something. Okay, 98 point. Yeah, correct. 98.29 Newton meter. This is the shaft torque that is available at the shaft end. That is the output torque. So, okay, the final question for today would be the efficiency. So, the efficiency we already derived. It is the total output net power, that is the shaft power, divided by the total input power, right? So, input power, it's already given in the question. Input full load, it is 12 kilowatt. The output is 10 kilowatt. So, the efficiency would be output by uh, input. So, the output is 10 kilowatt motor, right? Exactly, 83.33. 10 by 12 would be 83.33%. Yeah, correct. So I think that's the last question for today. Okay, so this, I hope you all have understood how straightforward these questions are. If you can have this information of the exact power flow diagram on your fingertips, it's pretty easy. And you also should have to get the idea like what all you have, what all they were asked, and how can you get a quick relation between these two. That's the logic here. So see, just knowing and understanding this power flow diagram is not enough. Like what you were asked and how you can get a quick relation, because see, in one of the question we were asked the air gap power at the full load, and quickly you have to relate that. Okay, if I know the input power, at a full load, I just have to subtract the stator losses to get the air gap power. So that kind of reasoning you have to be quick at while solving the problems. Apart from that, it's nothing but a mere substitution problems. So that's what. Let's have a quick summary. Some of joined very late, so you can also see what we have discussed and what I have started the today's discussion with. So in the last week we have discussed till the point of deriving the three-phase induction machine equivalent circuit, per phase equivalent circuit. So I've started the discussion with that today. That the top circuit is the equivalent circuit referred to the stator side, which is having a parallel branch of XM. Now to simplify it for the calculations, we did the Thevenin's analysis, and this is the Thevenin's equivalent circuit. So it's just all the series resistances and reactances in series now with Thevenin's voltage. So we derived the expressions for Thevenin's voltage and also the Thevenin's impedance to find the rotor current flowing through the circuit. Rotor current referred to the stator, that is I2 dash. The aim behind this derivation is to calculate the power and torque of the motor. You know the current, and we then proceeded to the calculation of power. But power, what power we are calculating? To understand that, we started with the basic approximate power flow diagram. We know the input, subtracting the losses in stator and rotor, you get the gross mechanical. So we derived the relation between these air gap, rotor, gross mechanical, and the slips between the machine, and we come up with this important and very key relation between the powers and the slips. And then we proceeded the torque derivations. So the torque is nothing but the power divided by speed, and we substituted the current expression in the torque expression to get the torque derivation. So once we get the torque derivation, we kind of analyze the torque slip characteristic of the motor, and how this torque, maximum torque, and also this the slip at which the maximum torque occurs depends on different parameters in the machine. That is, how does it depends on Thevenin's voltage, how does it depends on the rotor resistance, and what happens when an external resistance is inserted in the rotor. So all that we have seen, and the different variations in the curves. The left side and the right side curve will clearly indicate on what factors this maximum torque and also the slip at which the maximum torque depends on. And you can see the movement of the curve from top to bottom and also the from the left to right as you vary Thevenin's voltage and also as well as the external resistances. So this clear understanding would help us in understanding like what parameter you need to vary in order to get different starting torques at the starting as well as the different maximum torques. So see, if your primary concern is to get a maximum torque, so let's say in one condition you got some maximum torque, you want to get even more than that, so then you just have to vary the input voltage. You just increase the input voltage, you can get the increased maximum torque at the same slip. Now if your concern is to get a maximum starting torque, so you need to vary the external resistance in the rotor. So make your rotor side available for you. So your construction of the motor is in such a way that you can easily insert and remove the rotor resistances. So such a way that you can get the different starting torques. So as soon as your motor accelerates quickly, you can able to remove that rotor, because in running condition if you keep on letting those external resistance stay, your rotor copper losses would be huge. So that's the idea here, to get the higher starting torque. At the starting you increase the rotor resistance, and once the motor picks up its speed you can remove it. So that's with the discussion we started solving the exact power flow diagram, including all the stator side and rotor side copper losses and core losses as well as the mechanical losses. In between we have two powers, that is air gap power and also the cross mechanical power. Finally the power available at the shaft would be the net mechanical power. So then we started solving the problems. So these are straightforward problems if you understand the power flow diagram. And this is the different parts at full load and at no load. So at no load you have to take care. So at no load it's not like you don't require any input power. You have to supply for the all the no load losses, that is stator core loss and also mechanical losses. So you need to supply for those. And and at full load you will have all the powers: air gap power, mechanical power, cross mechanical, and all the conditions. And once you know what you want to calculate and you write the formula for it, and see whether you know all the parameters in that formula. If not, quickly you have to bring up some relation between the quantities, unknown quantities and known quantities. Like this problem where they were asked us to calculate the full load speed, in which you don't know the full load slip. To quickly get the relation for slip and powers, you got that ratio relation. So that's how you have to be quick in getting the relation, and then it's just easy, simple problems. So we calculate on this speeds, torques, and powers, and finally the efficiency of the machine. So yeah, that's all for today. And if you have any doubt or question, please ask, and we can discuss it now. Any question, any doubt related to this week or previous weeks, any confusion you have, you can ask. You can ask now. You can discuss. Even if I'm not able to answer it right now, we can I can look it up, and you can raise the questions in discussion forum also. So you are asking at slip at maximum gross mechanical power. Yes, this is, let's go back to that particular circuit. Yeah, here see, gross mechanical power. So if you can able to get the torque, mechanical, your torque, mechanical electromagnetic torque is directly dependent on the air gap power. Now if you are trying to make that particular torque maximum, we have to make the air gap power maximum. So whatever slip I have discussed here, so that is the slip at which your maximum electromagnetic torque would be maximum, that is your air gap power would be maximum. So if you want to maximize the gross mechanical power, so that slip will be different. So that is not the slip at which your maximum mechanical power would be, gross mechanical power would be maximum. So this particular slip is at which the air gap power is maximum. So for that, you have to, the analysis would be different. So I don't think that's of important now, because if you want to solve that, you need to go back to your equivalent circuit and you have to see what would be your equivalent circuit at which your gross mechanical power occurs. So, but from the power flow diagram and equivalent circuit, if you see, we kind of come up with this. See, maximum power transfer theorem, where you know this, in order to make this PAG maximum, this load impedance should have the same as source impedance. So that's it. I don't think they will ask like what is the slip at which maximum cross mechanical power occurs. That's not something of interest. However, you need to make the output maximum, that is the electromagnetic torque. It should be maximum. So if you want to maximize the electromagnetic torque, you need to go back to the expression of electromagnetic torque, which is nothing but the air gap power divided by 2 pi ns. So there's a constant 2 pi ns. So since it's directly dependent on air gap power, you come up with this. So that's it.
ஏம்மா எல்லாத்தையும் வச்சுட்டு போறீங்க? வந்துட்டேன். அத்தியாவசியமான பொருளே இதுதான். அத்தியாவசியமான பொருளே இதுதான்.
You can mute yourself.
வாழைப்பழம் இருக்கு.
Okay. If you don't have any doubts, so that's all for today.
என்னப்பா வண்டி எடுத்துட்டு
Thank you all
போறியா?
for patiently uh,
என்ன
listening to the discussion and participating in the
என்ன
discussion.
பண்ற?
So we will meet next week, Tuesday, 6 p.m. So meanwhile, I would suggest you to attend the other two TA lectures also. The concept which we have not covered in this tutorial session will be covered in the other two tutorials. So yeah, meanwhile, if you have any doubts or something, please keep raising your concerns in the discussion forum. We will get back to you. Thank you, Dinesh. Thank you.